All right. So your radio observation has come back, and now we have to turn it into an image. Your observation is a collection of data points. As the telescope is moving around, it's collecting data, it's collecting a spectrum at every point. But how do we turn that into an image? Now, in the previous video, we went to this link. So here I am at the observations page in Skynet. Under radio observing, you click on the observation, you come here. And the first thing here is the link to the preliminary data products, and these are produced by Green Bank Observatory. And in the last video, I talked about what they all are, and we'll use information from here to inform us as we're making final images. Now, on this page, you see some images, but they're preliminary images. There are 4 major things that can be wrong with them, and I discussed that in the previous video. How do we make final images, correcting for these common defects? So for that, we're going to use an algorithm called Radio Cartographer. This was developed by the Skynet team over a period of about 4 years. It took a while to do this. And I think it might be the best algorithm out there for single dish radio telescopes, for making pictures with single dish radio telescopes, which is like saying we are the expert in something nobody does. Because if you're going to make a picture at radio wavelengths, you want to use an interferometer. Remember, single dish telescopes blur things out tremendously, and so you use an interferometer. Very few people do images, mapping and images with single dish telescopes. With some of the larger ones, they do. And I think this is the best algorithm for that, and we'll be using it with our smaller single dish radio telescopes. Okay, so we have a lot of boxes here, and we need to go through them and understand what they do. I should say, if you come here, like I just did here on this page, this is the Jupiter observation. Everything's grayed out. That means someone has processed it previously. You have to press this button to create a new job, and then all the buttons open up. Okay, I'll come back here. This is the Virgo observation. So the first one is just called job's name. I think default, it says RC job. You can put anything in there. You know, if you end up running this multiple times with different parameters, this might help you to distinguish. Or if many people are processing the same data set, maybe you put your name there to show this was your processing of it. Anyway, you can put whatever you want there. It just goes into the name of the final file. Now, the next box here, the first important box, is image processing basics. Okay, so let's talk about what these things are. Under channel, you have X, Y, and sum. So back in the preliminary data products, we have 2 channels. Here's the Y channel, here's the X channel, and you just got to look. Are they both good? They both look good. Sometimes a channel dies, and if it dies, you'll want to use the other one. If they're both good, you'll add them together. You'll sum them. Because why not? Get twice the data, beat the noise down. This next one is gain calibration. That's referring to the noise source. Remember here, we have a noise source at the beginning and a noise source at the end. And we use the noise source to calibrate our data. So it's consistent with other observations, at least taken within a day or two. Well, you have the option. You can use the first one, you can use the last one, or you can use both, interpolating between them. You almost always want interpolated, though every now and then there's something wrong with the pre or something wrong with the post, and you may have to go back and just use one or the other. Again, it's redundancy. We have 2 in case one of them's wrong, one of them is bad. But try interpolated first. This one is image coordinates. We collected the data in equatorial coordinates, right ascension declination. But it's not like an image from an optical telescope. This is just data with coordinates. We can, and we are making an image from that data. We could make it in different coordinate systems. I could take my equatorial map and make it in a galactic coordinate system. We'll just stick with equatorial map. Finally, this corrects one of our 4 problems, the time delay. If you remember here, we have this zigzag problem. There's some kind of offset between recording the flux that we're measuring and the position of the telescope when we measured it. There's some kind of temporal offset between those two, causing this zigzag. And that's explained in the previous video. If you set it to auto, it will measure it from the data itself. As long as there's something in your image bright enough to latch onto, like this one right here, bright enough to latch onto, we can measure the time delay and undo the zigzag, making it a nice round source again. Now, sometimes that's harder. For example, here's an image of Jupiter. I'm shooting this video for both the Moon team, Module 1B, and the Jupiter team, Module 1C. Jupiter is really, really faint. You can see it here, barely in the preliminary image. Here, barely. Comes out better in the final image. But this may or may not be enough information to figure out that time delay correction. We'll talk about that in upcoming videos. If there's not enough there to get a good time shift measurement, you may have to play with it. But for the moon, the calibration sources should be easy. We can measure the time shift. So start with time delay auto. It will try to do the time shift. And if it's a bright source, it will do it no problem. If it's something faint like Jupiter and there's nothing else in the image to help it, it may not get it. Right here, include raw image. It doubles the processing time, but these run really fast. And so you can see both after all of our corrections and before. Okay, those are the basics. Next, the frequency range. What frequencies do we want to use? By default, it should be set to the full frequency range. For these observations, we observed from 1355 megahertz all the way through 1435 megahertz, the protected H1 band, so an 80 megahertz range. And we're going to want to use all these frequencies except for the ones we don't want to use. And those would be the ones that are contaminated by RFI. Which ones are? Well, we can look at the preliminary data products. This was explained in the previous video. Here we have the spectrum, and we're looking for these spikes. These spikes are potentially problematic. Now, this spike here at 1420, that is not RFI. That's cold neutral hydrogen. We don't need to cut that out. That is spread fairly uniformly across our image, and so it will subtract out when we do the background subtraction. Of much greater concern is this one here at 1381. You can see the effect that it had. And so if we can snip out this frequency, then all that disappears. Another common one is on the hundreds. And this really isn't technically RFI. It's a property of the electronics. It gives us a little glitch at 1300, 1400, 1500, 1600, and 1700. I'm not sure why, but we'll treat it as RFI and remove it. It's usually pretty faint. If you ignore it, it shouldn't be that big of a problem. But this one is problematic. Let's get rid of it. So I'm going to go back to this page, and you want to turn on skip frequencies. And to get rid of the 1381 line, I'm going to have a min skip frequency of 1380 and then go to 1382. So like -1 and +1. And that will cut out the 1381 line. To get rid of the 1400 glitch, I'm going to go from 1399 to 1401. So I'm going to cut out anything in that range as well. Again, we don't have to cut out the hydrogen. Now, if there's anything else in here, those are common ones, but there may be an uncommon one. As described in the previous video, you can go live, click on the zoom, and zero in on any part of the spectrum and do a careful measurement. And then you can add another row here and cut that out from one below to one above. Okay. Now, this part's a little bit more technical: contaminant cleaning and surface modeling. Three things here. The first thing is the background. We're going to subtract out the background. As I mentioned before, the background is dominated by Earth emission. We see the scanning effect in the background. We'd like to get rid of that. And so we're going to do some background subtraction. Now, I'm not going to get too technical, but let me show you what's going on. Here at figure 12, here's one sweep, one scan of the instrument going across the sky. You see the intensity. We're scanning over a source. Imagine a little bar. You can see it right here. If the bar is big enough, it doesn't really fit up in the source. If you're, imagine a little bar underneath and you're trying to slide it up, it will run into the background, but will have a hard time working its way up into the source. So we have an algorithm that tries all sorts of different ways of jamming that bar up in there, and you put them together and you get a nice background. And we'll then subtract this out. So the background level will become 0, and the only thing that will be above the background are the sources. And this helps to bring them out. It gets rid of the scanning effect. It gets rid of a lot of that elevation dependent background. Up here. So we start with background subtraction. And the key parameter is 6 beams. How big do we want that bar to be? It should be about 6 times the beam width, and it will do a good job for point sources. Okay. The next bit is RFI removal. Now, we removed a lot of the RFI by cutting out those bad frequencies. But there could be low-level RFI at other frequencies that we didn't notice. There could also be broadband RFI, meaning someone illegally transmitted it all the frequencies, boosting everything. And that would have been hard to see on the preliminary data products page. So in addition to cutting out the really bad frequencies, we have another way of removing RFI, and it's a spatial recognition algorithm. Like looking at this, I know that's RFI. Everything from space is blurred out the same amount in all directions. This is quite long in one direction, but quite narrow in the other. It did not come from space, and it's along a scan. So it's definitely RFI. These little blips here did not come from space. They didn't go through the optics of the telescope. And so they didn't get diffraction blurred. They just kind of worked their way into the receiver. And so we can use this spatial information to remove it. And without boring you with the details of the algorithm, let me show an extreme example. This right here. This is taken with a different telescope. This one moves up, down. And when pointed towards the southern sky, it's pointed towards Roanoke, Virginia, about 100 miles away. And in the Roanoke airport, there's a transmitter. It goes beep, 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 and it's polarized. It only messes up one of our 2 detectors. And this is the one it messes up. You can see here it is, beep, 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 beep. And then we get to the top and turn around, beep, 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 and it just continues through the whole map. It's not always on, but when it is, that data is wrecked. You may think you have to throw it away and start over. But using just our spatial algorithm. We didn't cut anything out in frequency here. Using just the spatial algorithm, all those little beeps are too small. And so we remove them and we end up with this. Well, is this right? Is it wrong? Are these astronomical sources? We can compare to the other polarization channel that's not contaminated right here. So yeah, it's not as good. There's a little bit, but that's pretty extreme contamination. A little bit does make it through, but it cleaned it up really well, given how bad it was compared to what it should be. And this is the combination of the two. So it's a really powerful algorithm for removing RFI, even if you don't cut it out spectrally. And that's built in there. Now, there are a number of parameters, but for you, you have two options, really. Faint target and bright target with airy rings. If you're looking at something faint, like Jupiter, use the faint target. It's a little bit more aggressive with the RFI removal. But for a bright target, let me show you another example. So here's a bright target. This is a Cassiopeia A, one of the last stars to supernova in our galaxy. Don't worry about the one on the left. The one here on the right, you can see a couple things. There's the bright target, but you also see little circles going around it. Those are called airy rings. And you see kind of these lines coming off it. Those are diffraction spikes. When you get to module 1D, we talk about diffraction spikes. As light works its way down to the telescope, it has to pass through these support struts. And light bends, that diffracts around these things, leaving what we call diffraction spikes around every point source. Now, most point sources are too faint to see it, but if you're looking at something bright, you can see the diffraction spikes. And here you can see them faintly, here, and probably one going through here. You can also see the light waves trying to bounce off the edge of the dish. It's a sharp edge. Waves don't like sharp edges. So you get diffraction rings here, here, here. And you'll see these things whenever you have a well-focused telescope. This is a well-focused telescope, optical or radio. You'll see these things. So they're not as wide as the point source. They're a little bit narrower. And you don't want to remove them as RFI. So it requires slightly different settings. And so for a bright source, instead of faint target, you select bright target with airy rings. So if you're imaging Jupiter, you want faint target. If you're imaging the moon, you want bright target. And for the calibration sources, whether it's Virgo A, Cygnus A, Taurus A, whichever calibration source you use, those are all bright targets with airy rings. And when you do that, it changes these other boxes here. And you don't really need to know the details of them. Those are the best configurations for faint and bright sources to get rid of the RFI that may still be in your image. Now, the last bit here is the surface model. Let's go back here. Let's go to image 4. Okay. So this is another representation of our data. As the telescope's going back and forth, it's measuring brightness measurements, and here brighter things are up in the third dimension. Now, we did not collect data on a grid. We moved as close as we could to a grid, collecting data as we go, but it's not like an optical camera where all the pixels are on a grid. We have data. We want to make an image of pixel data on a grid. So we figure out where those pixels are going to be. We pick a size for the pixels. The default is 1/20th of a beam. And around, let's say that red dot is one of those pixels. Then around it, within kind of a 2-beam region around it, It fits a model to the surface. It's a flexible model, and it's weighted to fit the center better than the edges. Here you see the edges don't fit well, but the center fits really well. So we do that fit. We take the value of the model at the red dot. That red dot is between the measurements. And then you go to the next pixel. All the pixels will be between measurements. And you use the surrounding measurements to model how bright it would have been at that pixel had we measured there. And you do that for every pixel in the image. And this is a superior way of doing it. A lot of people, they will move through the image kind of averaging the data, but that blurs your image out even more. And single dish radio telescopes are already blurry. This is a nifty technique we came up with, and it won't blur your image any more than it's already blurred. Okay. So you have two settings to worry about here. Well, one setting, two options. Measurement quality image, display quality image. If you're planning on making measurements from your image, you should go with the measurement quality image. When it's doing these little surface fits, it more strongly weights the center, getting the center even closer to right. Though the image can be a little noisier. If you're trying to make a picture for presentation, not for measurement, you want 2/3, which is the display quality image. They're not very different. It's a very subtle difference. But anyway, this is about filling in the gaps. So we have an image that looks like an optical sensor, a grid of pixels, two-dimensional grid of pixels. Okay, so everything is set up. I'm just checking, right target, measurement quality. So press the Let's Go button. And so the job is pending. It should only take about 10, 15 seconds, but I'll use this opportunity to explain why that's the Let's Go button. So this was coded by one of my undergrad programmers, Reed Fu, who we've determined has a limited number of emotional states. When he's excited, he says, "Let's go." And since this is an exciting process, he named the button thusly. When he is surprised, he says, "Ooh." When he's aggressively disappointed, he says, "Boo." For a while, we thought those were his only emotional states. We learned there's a fourth one. If he sees someone make a mistake, he says, "Destroyed." Like if you try to open a door, but it's the wrong door and doesn't move, and you should know better, you were destroyed. And we recently discovered he has a fifth emotional state. He's a programmer. If you ask him to edit the Skynet database by hand, which is something no professional would do, it elicits a 4-letter word response that I'll spare you from. Anyway, my favorite emotional state from Reed is "Let's go." It means he's excited. So let's refresh the page here. Have to refresh it. It doesn't update on its own. You refresh it, it's now complete. And if you do multiple ones, they're all listed here. You just click on whichever one, it restores your settings to that particular case. If you want to do a new one, you press this button. Okay. Once something is done, you can download it. Okay, it's been downloaded. And now we're going to upload it into Afterglow. So let's go to Afterglow. Going to open files. Going to upload. Here it is. Okay. Close it. And you find it in your list and you open it up. Okay, so there it is. I already had it open, but you get the idea. Opens up a grouped file that has many layers. If you click on the group layer, it's just a confusing combination of all of them. Don't do that. The first layer is your processed image. And look at how much better it is than the preliminary image, which has the zigzags. It has, you can see this RFI here at the top of the image, background variations. It's all cleaned up. It's all gone nice and smooth. There is a little bit here, and that's actually a real source. That's another galaxy. It's just coincident on the sky. That's another supermassive black hole, same as this supermassive black hole at a core of a galaxy. Now we can edit the brightness and contrast settings. So go to display settings. And if you want to see the fainter structure, go from linear to maybe hyperbolic arc sine, starting to see that diffraction ring, or square root. You can really see the diffraction ring there. I also usually like to hit bright target so the center is not super saturated. Okay, just a few more things here. This is the main object, but what's in these other layers? Go to the next layer down, you see the path map. After we've done the time shift correction, after we've done the zigzag correction and moved all the reads, all the places on the sky where we read data, we've moved them into the correct positions. And also a few data points have been removed. That's the RFI removal algorithm. It sometimes takes a few points around the base of a source, but doesn't significantly change the image. We can skip over the remaining layers down to the bottom layer, and this is the raw image. This is if we process it with no zigzag correction, no background subtraction, no RFI removal. And so here you can see what it would look like. And here you have the final product. All right. Now, if you imaged Jupiter, I believe I have that here. In this case, it turned out well, but sometimes it doesn't. If you image Jupiter and there's nothing there, you may have to modify some of the parameters. We'll tackle that in a separate video. That's the end of this video.